Okay, any questions?
I was slightly hold out.
Yeah, yeah.
Just going through the deviations are like that R 1 by x minus 1 are not clear very well. Like the ring, how do you first of all compute R 1 by f suppose. So first we'll replace x by 1 by f, that then we divide, right? That's how we do it, right? Because RF is defined as all f by g.
You want the valuation for 1 by f, 1 by x.
Any 1 by f, that one. Like we showed that when we go like inverted, only 1 by x is allowed.
Mm-hmm.
That one, calculation not very clear to me till now. I was going through it again.
So 1 by x was special, that was the point at infinity.
Yeah, for that we just do x, substitute x by 1 by y, and then we look at it like same way as rx, ry then, right? That's the way we look at r1 by x. How is r1 by f look like?
1 by f I don't remember. We didn't have that.
All the valuations are rf or r1 by x, right?
Yeah, so 1 by x was the only one which was special.
And why can't there be any other like that?
Oh, that was a proof, yeah. That proof we gave.
X belongs when this argument was there. If x does not belong to the ring, then we show it is always 1 by f of x in.
So we characterize that this one. Distinct DVRs are yeah, so RF is clear. That's like x minus alpha basically. For algebraically closed field, small k, it is just, you just look at the multiplicity of, I mean uniformizer is x minus alpha.
And let Rx, and must we just do x equal to 1 by 1, then look at Ry.
Yes.
The denominator has high degree than.
So either that, or now with in hindsight, you can just think of this as z equal to 0. Z equal to 0 is the point at infinity. So if you write down all the polynomials in x, y, z, then you look at the multiplicity of z.
And so then this 1 by x minus 1 thing.
Oh, this proof, yeah. So what? Okay. Suppose this gives a valuation, then so valuation of 1 is 0, but valuation of 1 should also be the sum of the valuation. Oh, but this is, yeah, this was nothing. No, I think it was later on that we got the correct one, which was you write x as x minus 1 plus 1.
Why is Vx 0 in this one? Not very clear, because we are looking at 1 by x minus 1. Right?
Yes, yes.
So
No, basically you want to look at either whatever valuation of polynomial f you are taking, either f or 1 by f, whether x equal to 1 is a root. In this case,
you showed first said that v of x is 0.
no, because x equal to 1 is neither a root nor a pole.
No, like for that I first have to see how does this DDR looks, right? R of this 1 by x minus 1.
Yeah, so that will be the same. Claim is that it will be the same as, you'd want to count the x equal to 1 poles.
I understand that, but like RF is a very clear definition, like divide, but R of 1 by x minus 1, also how do you even define the valuation? Like just set that.
Well, x is a unit there in that DVR.
I can't see the DVR, that's the problem. I can't see why is.
So if you call 1 over x minus 1 t, then x is what? 1 plus 1 over t. And
I'm just showing that x does not belong to the DVR minus 1. How do we think 0? Not clear.
no, 0 would mean that it has to be a, it has to, basically you have to show that it is outside the maximal ideal, yeah. In other words, 1 over x minus 1 should not divide this.
For that, first we'll collect all the x minus 1 powers from g and h and then look at valuation, right?
Mm-hmm.
That's how we do for x. For x
Mm-hmm.
minus 1, I'll do same thing. Something like that.
No, no. So, well, what is x minus 1? What is the valuation of 1 over x? Actually, that also you have, yeah, you have to calculate that. So, in this case, you have to collect well, when I wrote this Vx equal to 0, I just assumed that you have to check the divisibility with x minus 1 inverse.
But what does that mean when divisibility by 1 by x minus 1 inverse?
No, divisibility by x minus 1 inverse.
For like the way we do r of
It means the definition of that is how many powers of x minus 1 divide h in the g by h representation.
no, for wait, the way rx is divided first we take all the power divided by like x divides g and f divides g and f divides h or rf. It's subtracted, right?
Yes.
But if we do r of 1 by x minus 1, then that's the same as r of x minus 1 only. When right, you just wording the sign same.
No, no, no. You have to go, valuation has to be defined for every function. Every function looks like g by h, and the valuation is x minus 1 inverse. How many times does it divide g by h? Which means that you look at, let's say just simply you look at how many times x minus 1 divides g, how many times it divides h. And
like say r of 1 by x is not defined like that, right? 1 by 1 plus x will belong to r of 1 by x, right?
no, no, that is all, that may be fine, but valuation has to work for every function.
I understand, but the way r of 1 by x is defined.
This is my definition for every function. For g by h, valuation of x minus 1 inverse is the highest power which divides g by h. So, if g is 1 and h is x minus 1, then the valuation will be 1. And if g is x minus 1 and h is 1, then the valuation will be minus 1. That's all. You just take the, you just intuitively you first define it for every function. Then from there you build everything else.
You're doing division in the function field then.
Yeah, yeah. Valuation is a thing for the whole function field. You don't need to look at the DVR. DVR actually gets automatic. Once you define valuation on the functions, DVR will automatically be those elements in the those functions whose valuation is greater than or equal to 0. That will give you the DVR, and the complement is the functions where the valuation is negative. They sit outside the DVR.
When we divide it by 1 by x and f of x divided by 1 by x, then we give a degree bond, like how large it will be, because one is a kind of power series division, right?
No, 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 not power series. G and H are
1
polynomials.
by x will look like a power series, right? Technically.
G by H are polynomials,
And
and what is the valuation of x inverse there is just check polynomial division. This is not any different from valuation of x. This is the thing we did for x. And since I mean x is not something special, you can do the same thing with 1 over x.
And this is, okay, suppose I take the polynomial 1 by 1 plus x. Now, what is r of 1 by, v of 1 by x here? V of 1 by x does not divide 1 and does not divide 1 plus x, right?
1 plus 1 over x. And the valuation with respect to x.
Valuation technically is 1 here. of 1 by x.
Sorry?
I want d of 1 by x. No, like 1 divided by 1 plus x. I was saying that.
Sorry?
1 divided by 1 plus x. This one.
Okay. So this, in this case, the valuation is 0.
No, but we take x out, right? It will be, that's the way defined, right?
Sorry?
The way it will be defined is like we'll take all the x powers out and it should be 1. Valuation is 1 here.
Valuation is 1 because
1 by x times 1 by 1.
in terms of point at infinity, yeah, this is actually z over z plus x. So z equal to 0 is a root, that's true. So valuation actually should be equal to 1. Okay, so what you do, 1 by x you take out and then do this. And this is a unit. I see. Yeah, so 1 by x is a nice interpretation. What is the interpretation of 1 over x minus 1 then? So you want to calculate the valuation of x with respect to 1 over x minus 1. So it gives at point level it is something like 1 plus infinity, right?
Z by Z.
This is the point. 1 plus infinity is the kind of the point.
Yeah, so that will be 0 then because x lies outside.
So 1 plus infinity, when you look at the function x, that doesn't vanish. So this way, this has to be 0 with respect to point interpretation.
Repeat answer and
Sorry?
didn't follow.
The point 1 plus infinity is the 0 of 1 over x minus 1. That's the point. X doesn't vanish at this point. While here the point was infinity, because I mean this is 1 over x, so 1 over x, infinity is a point, is a 0 of this 1 over x, right? And it is also a 0 of 1 over 1 plus x, because 1 over 1 plus infinity will also vanish. So clearly the valuation of this function should be at least 1. And then for algebraic reasons it will be exactly 1. But here the valuation has to be 0, because so it can't be positive, it can't be negative, right? So 1 plus infinity, 1 plus infinity, the point is neither a 0 of x nor it's a 0 of 1 by x. Wait. 1 by x, it's actually a 0. Oh. That is true. So then it's actually minus 1.
That's what we proved. That's the minus 1.
Okay. See. So that reasoning is wrong then. I have to correct that. Yeah, it's not 0, so then it's coming out to be -1. So okay, so we have to actually then properly argue why isn't 1 plus infinity. I think it seems to me that this is the same, it will give you the same valuation as point at infinity. Maybe that would be the correct argument. So 1 plus infinity is the same as infinity.
So when
So-
you invert function, you will always get at z equals to 0, it will be equivalent.
Yeah. So I think
All the functions are pointing
I have to
z.
replace this orange argument by the argument that actually 1 over x minus 1 will define a valuation, but it's the same valuation as 1 by x. So the distinct valuation claim is still true. Yeah, let me do that separately. That's a good point. Yeah, it's actually not ruling out valuation. It's just saying that valuations either come from an actual point or from point at infinity. Everything else gives you one of these. Any other question? So then let's so last time we started the zeta function of smooth projective curves. So yeah, so our interest is in point counting since day one, which is that we want to count this big N sub small n, which is the number of points on the curve in a desired finite field, which is of size q raised to n. Right. So how many f q raised to n points are there, which means that both the coordinates should be in this field. So we know by algebraic closure that in f q bar, for any fixing of x, you will get fixings of y, possibly many. That was the cover of the projective line. But then that doesn't tell you anything about finite fields, because in finite fields, maybe when you fix x, usually you don't get y. So we actually want that estimate to be made much more precise. The covering of the projective line, how good it is it for finite fields? That's our goal. So we'll gradually move towards that by defining this zeta function and studying it. So we prove some properties. The zeta function version will be this. To begin with, it's just a formal power series in one variable t integral coefficients, and goes over all divisors. Okay, this is why we spend so much of time on divisors, because actually zeta function will be defined like this. Now, why do we take t raised to degree of d? So for this, you have to recall how the classical Riemann zeta function, the first one, was defined. It is sigma 1 over n to the s, right? So, and it goes over all the numbers. Now, in our curve world, the numbers are somehow simulated by divisors, but then the divisor group is not a multiplicative group, it's an additive group. So we put it in the exponent. Okay, so we change Riemann's original motivation slightly here, but the spirit remains the same. So we put t raised to the divisor, so that when you add divisors, this summand multiplies. Okay, so this is the correct analog of numbers. Yeah, and you can see that this is actually this. You can now try to recover classical theorems like this. Euler formula can be recovered. Zeta function factors into points. So that expression is the same as 1 minus t raised to degree of a point inverse. which expands this way. Right, so just like numbers factor into primes, divisors factor into points. So zeta function also has a corresponding factorization.
But those points go over the algebraic closure.
I don't think so. Our base field small k will be of choice. But so the point P is may not be an actual point, it's just a cloud of points.
It's a prime.
These are point with their all conjugates. It's a prime ideal if the, I mean, in general when small k is finite field. Otherwise it's an actual point when small k is algebraic closure. Accordingly, degree changes. In fact, we will do this very systematically. Soon we will actually calculate how the zeta function changes as small k changes. So these things you will see explicitly. We introduce this delta, which is the image of degree map. On the class group, degree map we don't know whether it's surjective or not, but we know that it's an ideal. And since Z is a PID, principal ideal domain, so there is a generator delta. So that number we will now keep track of. So we have the following exact sequence: degree 0 class group, arrow class group, arrow delta. Delta multiples. This is exact. Okay, so next we started expanding the zeta function. So we'll do this even more today. We will keep expanding it into something we understand. So definition is sigma over all the divisors. So you can write, first you parameterize on the degree, pick a multiple of delta, and then degree D class group you look at the classes, that's fancy D, and then in fancy D you pick a divisor, right. So clearly in fancy D, for whatever D you pick, the degree is small d, it doesn't change. And now we study the two inner sums. So basically what is the size of fancy D, that's lemma 1. And there you see that this this L sheaf which we had defined already appears. Okay, so we showed that this is basically equal to q raised to dimension of the L sheaf. So we get that formula, and next we look at how many classes are there of degree D, that's lemma 2. So we showed that it's the same as degree 0 class and it's finite. Okay, so those are the two lemmas, and we can now collect that.
So that is the space of all divisors, effective divisors linearly equivalent to
CLD,
it was just the
CL0.
space that you wrote down, your fancy D.
Oh, fancy D is just an element in CLD. It's it's a representative divisor, but it's not alone. So fancy D will have many other divisors.
CLD is within that divisor group modular degree, right?
Exactly. So you go over all the degree D divisors, but then you classify them into classes where in every class, if you take big D and big D prime, their difference is a principal divisor. It comes from a function. So the number of classes is finite, and also the size of a class is finite. That's what we have shown, lemma 1, lemma 2. So which means that now we can expand the zeta function confidently. So let's do that. Okay, so we'll call this number, since it's finite, and it's equal to all CLDs, a special name. So this is called the class number. The class number of C over the field of choice, small k. And it's denoted by HC. So this number is of course originally motivated from algebraic number theory by the works of Dirichlet. So every transcendence degree 1 function field has a class number HC. We call it HC. So what does the zeta function become? So this is the triple summation degrees are all non-negative, so multiples of delta, natural numbers, then you have the class, and then you have the elements in the class. Oh, and the sum always goes over divisors that are non-negative, right? So not all the elements in the class, but only the non-negative ones. Don't use negative ones. That we have counted. So this is equal to we just count t raised to d, so we have shown that it's this L dimension. And now we have to recall Riemann-Roch theorem to estimate L of d. What is L of d? So L of d is related to the degree of d, which is d, but then there is a difference is given by genus, right? So let's recall what that is. So LD minus DD is less than equal to L0. So basically, let's just say t is greater than or equal to 0. So from that, the L minus D difference is smaller than that for 0, which you know is 1, meaning that L of D is less than or equal to D plus 1. Okay, so we get at least an upper bound. We have still not used the full force of Riemann-Roch, that we'll do later. So for now, we just want to upper bound, I guess. So you will get the upper bound of this. So ZT is less than or equal to, maybe let's do next page. Okay, so the class number we get because that is the count for fancy Ds, and the second thing we are approximating is this Q expression. So the Q expression basically is, you can just expand it out after division. So you have Q raised to L minus 1 plus L minus 2 dot Q raised to 0. Right, so you have L many things, which is upper bounded by D plus 1. So you get definitely a lazy bound is D plus 1 times Q raised to d. So d plus 1 times q raised to d, and t raised to d sits there as the monomial. What do I mean by less than equal to? So this less than equal to, just think of this as comparing the coefficients of the monomials. Okay, it's z of t is actually a polynomial, and when I write this z of t less than equal to another power series, power series less than equal to another power series, I basically mean that I'm upper bounding the coefficients. I am not evaluating it, it's still a power series. So this upper bound we immediately get, and so we can now write down a proposition about how this power series converges. So z of t converges for which complex t's? What can you say now? Now in this power series, if we start actually putting complex values to t, when will this infinite series converge?
What t less than 1 over q?
Yeah, so if this hc is obviously a constant. Is this qt raised to d essentially which is growing very fast? You can also ignore d plus 1. It's only qt raised to d which is growing exponentially. So that's the thing which you have to kind of make sure that it keeps getting closer to 0. So for that, it's equivalent that qt should be less than 1. So that's the condition. Right. So the convergence is equivalent to the absolute value of t, or the radius of this t, which is a complex number. It should be strictly smaller than 1 by q. Then qt is less than 1, and you can show by easy complex analysis that this will converge for all complex numbers. That's the radius of convergence. And second is to compare with classical zeta function of Riemann, we'll sometimes substitute t by q raised to minus s, where s is a parameter or s is a variable. It's a variable which you can think of taking complex values. So when you put q raised to minus s, then for what s will this converge? So now you have to look at basically q raised to 1 minus s. So what does that give you? Q raised to 1 minus s should be falling, which means that the real part of s should be greater than 1. Right. So if the real part of s is 1.1, then of 1 plus epsilon, then you get this 1 minus s to be essentially minus epsilon on a complex part. But that is enough to let it fall and converge. The series will converge. Okay, so yeah, so the proof I leave as an exercise. And what this proposition tells you is that we can view the power series Z also as a complex function. right? So if we wanted, we can actually, we started with a formal power series, but if we want, we can also view it as a complex function. It takes complex values and converges to complex and under assumptions on the argument. I guess it's not, the domain is not everything, of course. There is some domain from that domain to complex.
Yeah, that's what you showed next. Meromorphic content. That's the rationality.
Yes, and it has a continuation, but that we'll not discuss in this course.
So the rationality is the continuation, right? You are essentially showing how to continue.
That's a good one. Yeah, so what's the continuation of this? Yeah, good. So it converges only for some part of complex, but suppose you wanted to extend the zeta function so that it converges for all complex, so that it truly becomes an analytic complex function. So whether it has a continuation, yeah, so it's an interesting point. We will come back to it again. Right now, it is not clear whether these things will happen. Okay, so with this proposition, let us define one more notation. So we denote this thing z of q raised to minus s as actual zeta. Okay, so this is the notation we'll use. That is where the name also comes from. So this will be the classical kind of notation for zeta function. Now for a curve, s taking complex values, and z of t will be our power series version. Yeah, that's one thing, and other thing is I want norms of a divisor. So norm of a divisor will be defined as, remember you had this t raised to degree of divisor term. So that is kind of the norm. Okay, and formally we define it like this. So norm of a divisor is simply q raised to degree. Why have we put q? Well, we have put q because to match with the definition of this zeta function. So instead of t, I am using q, so it actually becomes a number. It's,
Formal parameter, right?
sorry, q is our old q.
Infinite field direction, that Q.
Yeah. Yes, so why are we using that q? There is a very good reason for it. Using the same q, actually, maybe you should also already guess that. So this formula that we had on the top, the approximation, right, upper bound, that has qt raised to d. So q will actually be that which came originally from this lemma 2 or lemma 1. So in lemma 1 we had this estimate, right? So whatever q was here, so that was the size of the base field small k. So that is the q which is hanging around everywhere. uh, its its consequence will be pretty big. It will actually give you the uh, kind of the analytic continuation of the zeta function. In other words, we will show that z of t defined as a power series actually converges to a rational function for all t, I mean for the formal t. Okay, so that rational function is the analytic continuation. So this q is important. Only this q will work. It's not formal. Um, okay, so this norm I have defined only to give you the comparison with Riemann's zeta function. So this zeta function is equal to sigma norm of d to the minus s and equal to by Euler's formula that holds here points on the curve. And they are all convergent. Okay, so for these complexes, they actually converge, and for formal S, you have this identity. The first equality is just coming from the definitions, right? So why did we write it this way? Because now you can see that Riemann's original zeta function is of this type, exactly. Right, so that's there is an analogy. So ordinary Riemann zeta function is zeta s sigma 1 over n to the s. Right, so for numbers, in the case of integer ring, you go over all the numbers. These are kind of your divisors, and the norm of that divisor is the number itself. So this is n to the minus s. Let's just write in that exactly that form. Right, so norm exponentiated with minus s. So it's exactly the same form. And by Euler's identity, you can express it in terms of prime numbers. It factors. Right, you can just match it to term by term and see that this is actually an identity. So for primes 2 or more, you have the same analogous thing happening. Norm of the prime is prime itself in this case. And it becomes a convergent series if your S is real part is greater than 1. Right, so you can recover the classical expressions, and of course you hope much more. You want to recover all the classical theories as well. Right, so that's what we'll do. So the next thing that we want to recover is what is called the functional equation and the symmetries. So I don't know whether you have seen, because I have not seen. the ordinary Riemann zeta function, the functional equation and the symmetries are not very easy, because you have to first give the analytic continuation of this, which doesn't assume real part of s greater than 1, and that's not explicit. However, in this our zeta function zt, we'll actually we get an explicit expression. Okay, and that will be thanks to Riemann-Roch. So we now show that z of t is a rational function. Further, it has a symmetry. Around s equal to half. Okay, so the famous Riemann hypothesis, that is basically this. It is conjectured by looking at this symmetry around s equal to half. So here the key idea will be, of course, Riemann-Roch. So because Riemann-Roch had also this symmetry, the divisor of speciality was basically W minus D, right? So that symmetry at the level of zeta function is what we want to now lift. And what will we get? So first is that Zt is in Qt. Although there was no reason for this to happen, because we define it as a power series. Almost all power series are outside Q of t. And in fact, it's even worse. Almost all power series are even outside algebraic closure of Q of t, right? Because they actually happen to be transcendental. So you can't really set up algebraic equations. So it's a very, very special thing that this happens. This converges in Q of t. So this is the answer to analytic continuation. Right. So answer here will be very explicit, the analytic continuation. So you can forego the power series and you can just focus on the rational function, and then you can evaluate it wherever you want. It converges all the time, except at the poles. Poles also we will classify. So everything will be classified. It will just work always. And second thing is very mysterious, that it satisfies this equation. So what this is saying is, you look at z, you look at the transformation 1 over qt. Okay, so how does zt compare with z of 1 over qt? And there is a nice expression, okay, which again there was no reason for this nice expression to exist, because even after you have rational functions, the ratio of two rational functions could be very complicated, but here it seems to be not. It's highly elegant. Okay, so let's prove these things. It's surprising that you can actually see the proof of this now. You have enough machinery for this. In fact, the machinery that we have developed till now is built exactly for this. Okay, you will see that almost everything that we built goes in this proof. So yeah, from the previous not proposition, but this place that we somewhere we had the expression, this blue expression. Yeah, let's recall this expression. We can write q minus 1 times z of t equal to appropriate degree and appropriate class, q raised to L of the class minus 1 times t raised to d. Right, that is what we have simplified. At least the innermost sum we have simplified. And now what we want to do is study the first part, which is the L dimension. So let's break it up. I mean, this will be nothing but just try to get this infinite sum to converge to a function, rational function. Right? We want to sum up this series. Now, how do we further break it up to sum the components? It is basically guided by this L dimension. So we have a pretty good control. The L dimension is basically the degree when in the cases when the divisor is big. Right? This we have seen many times because of Riemann's theorem. And then we made it even more quantifiable by Riemann-Roch. So we showed that essentially when the degree is at least 2g minus 2, in that case we have a formula for L dimension. And when the degree is smaller than that, then we don't have a formula. So we break the sum into two parts accordingly. Yes, so first part is Ft, which is the good part. So that is degree greater than equal to 2g minus 2 plus delta. Yeah, degrees have to be multiples of delta. So it's that delta we are using. So q of LD t raised to d minus the other infinite part. And the other part is GT. So that's the finite part. So this part is messy, but it's finite, so it's okay. Yeah, did we lose anything? So this GT goes up to 2g minus 2, and then FT starts from 2g minus 2 plus delta. Did we lose anything in the middle? Well, we did not lose anything in the middle because remember that 2g minus 2 is the degree of the canonical divisor, right? So in particular, that was a multiple of delta because every degree happens to be a multiple of delta. So 2g minus 2 is some multiple, and the next one will be plus delta. So we are doing it in increments of delta, so it's fine. So the function can be partitioned into these two, and yeah, recall basically that for canonical divisor, the L dimension is g and the degree is 2g minus 2. Which means that 2g minus 2 is a multiple of delta. Okay.
Oh, this delta is the generator of the image of the degree one.
Correct. Yeah. So degrees of all classes go in multiples of that. We'll prove in the end using the zeta function that delta is 1. Right now there is no way to prove it because as I said, base field small k can be finite field, and right now you have no idea whatsoever how the points are distributed in this finite field on the curve. In fact, your curve may have no point at all from there. So there is no way to say that there is a point of degree 1, for example. Right? I mean, degree 1 points are the real points in your base field, but there may be no such point, because all the points they are in the algebraic closure, and you don't know where. So we are actually working in the blind right now, and we'll come out of this darkness only once we have proven the Riemann hypothesis. Only then will we know that in every finite field, essentially, you have a lot of roots. So lot of degree 1 points. Okay. So yeah, but let's continue with this delta, formal delta, the unknown delta. Yeah, so when the degree is more than the canonical divisor, then you know that L of W minus D is nothing, right? Because I mean, W minus D essentially is a negative degree divisor, so you cannot even have constant functions greater than or equal to that. So there is no function whatsoever in the L sheaf, which means that or maybe use this fancy one. Yeah, so which means what about L of D? So L of D is then simply given by the degree plus 1 minus G. Right, so this this what was that called? Degree of speciality is 0. So you get just difference is exactly 1 minus genus. That's a good situation in our formula. So we just plug this in f of t, and you will see that it will get very easy to calculate, because what you will get essentially is, I mean, degree is just d, so you will get qt raised to d, and qt raised to d you can sum up to d infinity, right? That is geometric progression. So this case actually reduces to geometric progression, and that is the magical part. So that was the hard part, what to do with the infinite sum. Infinite sum actually reduces to geometric progression, and you have a rational function. GT is the finite part, so it cannot disturb, right? So you have convergence that way. But we can't stop at this because we have to prove symmetry also. So we actually have to do the calculations to get the symmetry. Symmetry is a more is a deeper thing. So let's do that. We can simplify, or we can sum up Ft like this. So Ft is equal to yeah, let's sorry, there is always this d hanging around, fancy d. So we have to go over all the degrees and all the classes. So let's use the class number formula here. So we'll get HC times, this is from Riemann-Roch, d plus 1 minus g, t raised to d minus HC divided by 1 minus t to the delta, and the sum goes over large degrees. And multiples of delta. Yeah, so we have removed we have counted the classes by putting this HC, and we have also used Riemann-Roch for high degree. So we have replaced L by d plus 1 minus g, and t raised to d stays. And what have we done with the second summand? Minus. So the minus sigma t raised to d, we again have counted by the class number, and the rest is just geometric progression. So it's happening in multiples of delta. So the geometric progression will give you 1 over 1 minus t raised to the steps delta. Okay. Yeah, and then we can just continue. So let's take out HC, q raised to 1 minus g, and get to qt raised to d. That's the geometric progression part here. Same conditions as before. Minus which will sum up to by geometric progression formula. So qt to the starting point, which is 2g minus 2 plus delta, divided by 1 minus qt to the delta. Okay. Fine. So that completes the proof that f of t is a rational function. And you can see the poles. So f and g are now in qt, which means that we have shown zt is in qt. Okay, this is the first major property. You can observe more interesting things here. For example, if you set t equal to 1, then the first part, then both the first part of f and g are obviously well defined values, except this hc over t raised to delta minus 1, right? It will go to infinity, and it goes to infinity with the residue, the class number. So you get we make this observation that the residue of the zeta function at t equal to 1 is the class number. Okay, so we'll collect these properties later, but you can already see these things happening beautifully.
It's order 1 over that.
Correct.
Three over.
Yeah, t equal to 1 and t equal to 1 over q and many others, possibly others.
Others are basically potentially the
Delta roots of unity in complex, yes. Yeah, so the interesting thing is that this calculation is happening over integers while our curve was over finite fields, right? So it's a characteristic change. But anyways, it's true that the residue of the zeta function at t equal to 1 is highly important. It knows about the class number. Okay. Yeah, let's go to the symmetry now. Under 1 over qt. So for that we have to repeat this calculation with the big F of 1 over qt, but also g of 1 over qt, and see that we get similar expressions. So big F of 1 over qt is class number times this sits, and
So numerator will become 1 over t.
Yeah, I'll do that in the last expression. Yeah, because that would be easier. I don't want to start from the beginning. Yeah, so last expression, when I put 1 over qt, then essentially the base qt becomes now 1 over t, and yes, and there will be changes in the negative part. So let's do that. So I get t raised to minus 1 raised to divided by 1 minus t raised to minus delta minus the residue part, and this becomes qt minus delta.
Will there be a q in the denominator?
Yeah, where? In the first part?
Yeah,
Yeah, so this is what I said.
okay, that's fine.
That's the beauty of first part. Since there is already qt sitting, so somebody great thought that why not just transform this by 1 over qt. So the first term doesn't change by much. So that should be a symmetry. Yeah, so let's verify it. You will get now qt square to the 1 minus gi take out. Let's check what remains. Yes, so what is happening is kind of these two summands, they are flipping. So I take qt square raised to 1 minus g, and I think this should be fine. I have multiplied above and down by t raised to delta, and same thing here with qt raised to delta I have multiplied. Yep. And I have taken a reciprocal of qt square 1 minus g, so that's g minus 1. And this you can now check is simply qt square 1 minus g times f. Okay, so f already has this symmetry.
Is there a minus sign?
Where?
Is that F or minus F?
Should be fine, because in the denominator I have make it 1 minus t raised to delta. So the two terms here, they have just actually switched when I applied 1 over qt, but then in the denominator also you have to switch them, so you will get back ft. Yeah, so big F is already behaving very well. This is just 1/2 of the zeta function. Let's check the other one. Is g of qt inverse. So where is g? G we never studied. So g was the finite part, right? Low degree, so Riemann-Roch is not, I mean, Riemann's theorem is inexact here. So we don't really know how this L dimension behaves, but we can still just substitute 1 over qt and see what happens. So this is the d less than equal to 2g minus 2 part. Yes, so here actually, since Riemann's theorem is inexact, we will actually use the full force of Riemann-Roch. We will actually need the relationship between this degree of speciality with the L sheaf of the dual, which is canonical divisor minus d. That is what will save the day. That's the reason for symmetry. So let's do that. So these degrees and their classes, fancy d, goes without saying that everything here is happening in multiples of delta, right? It's all implicit there. And the new thing is that degree is at most 2g minus 2. So you have to be careful that when genus is 1 or 0, then this doesn't make sense. So these things are vacuous, right? But those can be checked separately. It's very easy. Just think of genus to be greater than 1. What happens then? Okay, so yeah, so let's write the Riemann-Roch in the exponent. So that's d plus 1 minus g L w minus d times qt raised to minus d. From here we can take out qt square raised to 1 minus g, which we want to use in the symmetry, and see what remains. So what remains is nice. Okay, so let's check qt square raised to 1 minus g. Are you convinced with this? So you have to use the formula that degree of W is 2g minus 2. So t raised, what we have there is t raised to 2g minus 2 minus d, right? And I have taken out t raised to 2 minus 2g and given 2 raised to t raised to 2g minus 2 there, and minus d was already present because t raised to minus d was there. So t monomial is correct. And now look at the q monomial and you can check that it's fine too, because d and minus d cancels and 1 minus g remains, which is out. Okay, so this is just a rearrangement of q monomial and t monomial. You can verify separately it's correct. And now what?
Just change the index. Run over every negative.
Yeah. So let's recall what G was. So G originally was Q raised to LD times T raised to minus small d minus degree, right? So this is equal to, let's just recall what this is. It's minus of, that's the exponent. So Q raised to L dimension and T raised to minus degree of that divisor class. That's the form here also. Wait, it's not confused with this. Let's go to the definition of G here. Yeah, so here let's just keep this as like this. So G is Q raised to L and T raised to D, right? So that is the form we have now. Q raised to L and T raised to D, and then as Madhavan said, as we are going over all the divisors, either you go over the divisors D or you go over W minus D, it's the same thing. You have the same space. So that symmetry will help. As D runs 0 to 2g minus 2, which is degree of the canonical divisor. Okay, so this so it's very important what the sum is over. Since the sum is over 0 to degree of the canonical divisor, W minus D behaves well. So you can switch it back to D. So this is all coming from Riemann Roch. So we need everything that we did there, which implies that G of Qt inverse is equal to Qt square 1 minus G times Gt. Okay, so both F and G independently have this symmetry. That's amazing. You didn't know when we partitioned the sum this way, which implies that Zt also has this symmetry. Right, so that's the full proof. So Zt is a rational function which under 1 over Qt is changes very elegantly like this. Any questions? Okay. And what about the zeta version of this Z? that also we can state. So zeta version in the above you have to substitute t equal to q raised to minus s. And you can just easily verify that it becomes this. So this is even better. Okay, so you can check that instead of t, if you use q raised to minus s, you get this relationship where so s goes to 1 minus s, then what happens is you are just multiplying by the norm of the canonical divisor, canonical class raised to s minus half. Yes, so at s equal to half, these two things are obviously equal. And then you can see that there is this symmetry around s equal to half. So there is a mysterious symmetry about the axis real part of s equal to half. Yeah, so here obviously we have a perfect explanation of this symmetry, which is Riemann-Roch. Do you know what is the reason for symmetry in ordinary zeta function?
Is that some gamma function?
Yeah. Yeah, but I don't think it is known what is the relationship between these two things. So these two seem to be totally unconnected at the proof level. But this half is there. So some syntactic comparison can be made. Yeah, the second corollary is so the poles of Zt are by the zeros of 1 minus t raised to delta, 1 minus q raised to delta, t raised to delta equal to yeah. And since we don't know whether delta is 1 or bigger, at this point we don't know how many poles there are, but they are of a simple type. Essentially t equal to 1 or t equal to 1 over q. And definitely they are simple. Yeah, so this is an important thing to remember, that we have shown that the poles of the zeta function are simple, because we are in characteristic 0, remember. So these polynomials, they have only simple zeros, because these polynomials are not powers of anything, they are square free. These are square free polynomials, right? Even if delta is very big, it's still square free. And something more we learned, which we can keep track of here, which is that at t equal to 1, the residue that we are getting is something like h, the class number divided by delta. This is the class number divided by delta, right? Because at as t tends to 1, what you are getting is obviously hc, and then in the remaining thing you have denominator has 1 plus t square dot t raised to delta minus 1, which evaluates to delta. So you get class number divided by delta. That's the residue. That's basically z of 1. This may not be a good notation. Let's just say z, the residue of zt at t equal to 1. Yeah, so when we know delta, we'll also know what the residue is exact. I mean, we'll know that it will be exactly class number then. So to finish that part, what we need to do is something fundamental about the zeta function, that is to understand how it changes as we change the field. So how does zt change as k changes? So that's called base change theorem. It will be relatively easy now. So let Cn be the curve obtained from C by extending previously it was q, size of the field was q, let's make it q raised to n. So extend small k to small k prime. Remember that the curve has coefficients from the field of constants fq. So it defines a curve over whatever field extension you want up to fq bar. So you can just go to fq square or fq cube or whatever fq to the n, and you will get these zeta functions which will be very different, right? Because morally speaking the divisors don't change. All that happens is the cloud becomes smaller. So previously there were many divisor, or a point was actually representing a bigger cloud. As you go to bigger fields, the cloud becomes smaller, because now the conjugates will actually separate out, and once you reach fq bar, then the cloud is just a point. There are no conjugates, right? So we are moving in that direction. So zeta function will change a lot because it was actually counting these things. So how does it change? So it changes like this. Zeta function for the curve Cn, if you substitute t raised to n there, then it factorizes. Okay, so once this is written down, you can see that it's quite natural expression. So you have zeta function for Cn with t, and you have zeta function for C with t, and the relationship is that in the bigger one, if you substitute t raised to n, then it factorizes into the smaller ones, where you are scaling up t by an nth root of unity. Okay, so it's kind of the factorization of t raised to n minus 1. So t raised to n minus 1 factorizes into or 1 minus t raised to n factorizes into 1 minus eta t. So same thing. Yeah, some version of that. So we'll prove this next time.